So let's get started with one example. This is a modified example 13.4. It's not exactly like this. It's I would say a simpler version. Assume you have a curved absorber surface. So let's call it absorber surface. You have a flat plate in front of it. That you have some dimensions of this as well. So this is W. And then remaining is whatever left is room wall. So I show it like this. This is room walls, which are everywhere, right? All around it. So in a manufacturing, the special coating on a curved solar absorber surface area A2. And by the way, this absorber has a surface area A2, temperature T2, and emissivity called epsilon sub 2. Is cured by exposing it to an infrared heater with W. So this is the infrared heater, IR heater. And the distance between the absorber and the heater is 1 meter. The upper surface of the absorber and the bottom surface of the flat plate or the heater are insulated. So, you know, there's a heat exchange in between, nothing beyond. So, the temperature of the heater, so this is T1, is 1000 Kelvin. And emissivity of this heater is 0.9. The absorber is at 600, so T2 is 600 Kelvin, and emissivity is 0.5, and epsilon 2 is 0.5. The system is in a large room whose walls are at 300 Kelvin. So let's call this T3, 300 Kelvin. And what is the net radiation of heat transfer to the absorber surface? So the question is net radiation. So the question is net rate of heat transfer. I'm sorry. Net rate of heat transfer to absorber surface, which is the curved surface. So if we can solve this one, we can solve any form of heat transfer inside the equation. So that's why I call it like one scratch. You should be applying the same approach to anything. And all of the equations you're going to see here are simplified version of this. So I put it this way, that to simplify this is not an enclosure, right? I have one surface here, another here, and everything else is the walls of the room. And now, to make this an enclosure, probably I can show it red. I'm gonna close this. If this is exactly, so those are supposed to be exactly on top of each other. So let's say if I close this and this, I'm going to do a better job. This should be exactly same size. Now I have an enclosure, right? These two are representing on walls around. So again, to imagine this, imagine you have an infrared heater. This is my infrared heater. On top of this, exactly the same size, I have the absorber curve, and then there is a room around us. So if I bound it like this with imaginary walls, and I can calibrate the properties of the same room walls around it. And why we can do this? Why we're allowed to do this? Because you can say, in terms of radiation, if a portion of radiation from the heater can go hit this wall, if I have this imaginary wall here, it's definitely going to hit it. So you can really assume you have your room wall here and then close your enclosure. Now we have an enclosure. And I have a three surface enclosure, right? I have heater, absorber, and room wall, which are the same. Now, because I have three surface enclosure, three surfaces, I need three radiosity nodes. So one node for the heater, one node for room wall, and let's say one radiosity node for absorber. So those are radiosity nodes. Now, I had this in class today. In radiation, we are dealing with two types of thermal resistance. One, thermal resistance is, you can call it surface thermal resistance, which is due to emissivity of the surface. 1 minus epsilon 1 divided by epsilon 1 A1. So if you have a black body, which is an ideal surface, emissivity is maximum, which is 1. So this resistance is 1 minus 1, which is 0. So if you have a black body surface, you are emitting the maximum radiation, so there is no resistance in front of that surface. If you have any surface gray body, which is not as good as black body in terms of emissivity, emission, then there is a small resistance because of that total emissivity. So for each surface, we should assign one surface resistance. That's rule number 1. And then we have another thermal resistance, which you can call it view factor thermal resistance, which is 1 over A1 F12, that between each two surfaces, we know that only a portion of the radiation from surface I leaves to surface J. So because of that portion, we can somehow model it with the resistance. So saying that because not all of it going there, then there's a resistance we can assign instead. Again, if view factor is 1, or we have two parallel surfaces like this, that 100% going to the other surface, then the resistance is 1 over A1. If the view factor is small, then I have a very large resistance. Now, I'm going to use these two resistors to build my network. This is, I guess we call this wall 1. So let's call this radiosity of surface 1, radiosity of surface 2, and radiosity of surface 3, which is room. Now, as I said, each surface ideally emits at its black body emissivity power, which we call it EB1, black body emissivity power of surface 1, and then that surface resistance we were talking about is in between of an ideal case, EB1, and the actual what's happening. And that resistance is nothing but 1 minus epsilon 1, A1. So for each surface, we should do the same thing. So for surface 2, for this curved absorber, I have EB2 emissivity black body power, and in between I have 1 minus epsilon 2, A2. That's the resistance in between. Same thing for other surface. EB3, and I have 1 minus epsilon 3, A3. So each surface in your enclosure gets one surface thermal resistance. Okay? Now we're done with those surfaces. Now, each two surfaces in enclosure gets one of those view factor resistance. Now, between surface 2 and 3, or between this curved absorber and the room walls, I have to assign one resistance, and that's equal to 1 over A1, not A1, there's no 1, surface 1 here, A3, F32. And if you remember the reciprocity rule, I can also say this is equal to A2, F23. They're the same. Right? Same thing for other two surfaces. So between J2 and J1, which is curved surface and here, I should assign another view factor resistance. And this is equal to 1 over A2, F21, or reciprocity rule, A1, F12. They're the same, it doesn't matter. Whatever data we have, we can use those. And then I have another two surfaces, so there's another view factor resistance in between, and this value is, we can use another color, 1 over A3, F31, which is equal to 1 over A1, F13. Now this is the network. Now the question is, what are our unknowns? We're looking for J1, J2, J3. So we have three surface enclosure, we have three unknowns. And EB1 or EB2 and EB3 are known, which are equal to sigma, Stefan-Boltzmann coefficient, times temperature of that surface in Kelvin to the power of 4. Same thing here. Sigma, which is a constant, 5.67 times 10 to negative 8. Temperature in Kelvin to the power of 4. And same thing here, which is sigma T3 to the power of 4. Now, there's a typical assumption is that the surrounding room is large and therefore behave as a black body. So you'll use this assumption a lot. So a typical surface, we know it's not black body unless it's fault, but surrounding, if you have an enclosure and everything else is really larger compared to this case. So surrounding, if they're really large, is large, and we can behave those, or we can treat those as a black body. What that means? Anyone? Surrounding, you can most of the time assume it as black body, which means that if this is surrounding, and if this is black body, that means that emissivity of black body is 1. Therefore, 1 minus 1 divided by this goes to 0. So there's no resistance from the black body, which is our surrounding. Now, once you build your thermal network like this, or any enclosure, any configuration, doesn't matter. Now, we have three unknowns, J1, J2, J3. We need to put a control circuit around those nodes. and write three equations. Three unknown, three equations, then we should be able to solve it. And believe it or not, you have to do it, even on those FE or PE exam. Looks like time consuming, but you have to be quick and do it. So let's take a look at, I'm going to use green. So this is one dotted line around radiosity J3, around radiosity J2, around radiosity J1. Now this is important here. T1. This is what we assume. At every node, you are assuming that radiation or heat coming from the black body power to this node, to this radiosity, and leaves a portion this way, a portion from other branch, which is typical, right? That's the energy balance. If energy comes in, a portion should be go this way, other portion should go that way. Now later, and we're going to do this for all of it, later we can find a negative number, which means that the direction was wrong. Or sometimes we see that this is zero, which means that all the heat is going this way. So we're going to find that rule as well. And same thing here. And this is zero, by the way, because is this shooting this is zero? For now, I'm going to show it like this, and then a portion lives this way, a portion lives this. So right now, I'm showing three equations, right? Comes in equal this plus this. Comes in equal this plus this goes out, and same thing. Now let me write it for node 1. So I'm going to write it for this. I have, I guess I have to go to the next page. So I'm going to write it for node 1. I can say sigma T14, which is black body emissivity power of surface 1, minus J1, which is unknown, divided by the resistance in between of those, which is 1 minus epsilon 1 over epsilon 1 A1, equal to 2 terms. Now, let's go back, make sure we understand what we're talking about here. So what we're saying is that EB1, which is sigma E1 to the power of 4, minus J1, divided by whatever resistance we have in this loop. And remember, from resistance, we typically had Q divided by resistance was delta T, right? This is in the form of thermal resistance network, works the same way. This is Q, EB1 minus J1 divided by resistance in between, which is this. So I have the left-hand side, and right-hand side, I should talk about this portion of the heat leaving plus this portion of the heat leaving. Now for this portion, since we're showing it's going this direction, I say J1 minus J2 divided by resistance in between. So I have J1 minus J2. What is the resistance in between? Is 1 minus A1 F12. And you help me with the other one.
J1 minus J3.
Exactly. Divided by
A1 F13.
exactly the resistance in between. So which is this second component. So J1 minus J3 divided by 1 over A1 F13 or reverse A3 F31. Yes. So this is one equation. And remember, we have to write 3 equations because we have 3 nodes, because we have 3 unknowns. Now for node 2, quickly here, so I can say EB2, which is sigma T2 to the power of 4 minus J2 divided by the resistance between, which is 1 minus epsilon 2, epsilon 2A2 is equal to this portion plus this portion. So quickly on this, I have EB2, which is equal to this, sigma T to the square, to the power of 4 minus J2 divided by the resistance between these two, which is 1 minus epsilon 2 A2. That should be equal to 2 branches of heat leaving, right? Which is one of them is this. Which the way we are showing this is J2 is higher, so J2 minus J3 divided by the resistance in between. Which is A2, F2, 3. And then another one is this guy, J2 minus J1 divided by the resistance in between, right? J2 minus J1 divided by 1 minus A1 F1 2 over A3 F1. Yes. And I'm going to write for note 3 quickly as well because that black body makes some simplification somewhere. So for note 3, we are saying that since 1 minus epsilon 3 divided by epsilon 3A3 is equal to 1 is equal to 0, because we said that surrounding we can treat it as black body. Why? Because epsilon 3 is 1. Then what happened is that if this is 1, if this is 0, there is no resistance, then whatever leaves from EB3 is equal to J3. There's no resistance to reduce it, right? So simply we can say J3 is already found, which is equal to EB3, which is equal to sigma temperature of the wall to the power of 4. So J3 is found. Now we ended up having 2 equations, 2 unknown on top, right? One of them is this, another one is this. So this is found for J3. And really, I don't want to go ahead and solve it. This is an example of the textbook. Now you have 2 unknowns. So of course you found J3 just by this, because sigma is 5.67 times 10 to the negative 8. Temperature of the wall was 300 to the power of 4. Whatever the number is, this is J3. That's one of the unknowns which is found. And I should solve this equation and this equation in order to find J1 and J2. Those are the only unknowns. Yes, sir.
On resistance on like 1 and 2. For the A, is it supposed to be like A2 or A4 or is it?
Which one?
For like either one on the left hand side of the equation. That A right there, is it supposed to be A1 or is it?
That should be A of that circle, which is 1 excellent. This is 2. Whatever epsilon takes should be that.
Okay, that's what I got.
Yeah, no, that should be this. That's absolutely correct. And if I go back, so this is should be 1, or whatever surface we're talking.
Okay. So maybe the third one was equal to 0 because it's the wall and it's the verse black.
So the third one was 0 because it was black body. We assumed it, or it's given. If you have a black body surface, you can't assign any resistance because of the emissivity, because the emissivity is mass. So there's no way. Exactly. So surrounding, if you hear the word surrounding in most applications in radiation, that means that you have to assume it as a black body.
So we didn't tell you it was a black body?
No.
We just need to know.
Exactly. And the part of the solution is this. No, we don't have even the word black body in this problem. under assumption, it says the surrounding room is large and therefore behave as a black body. So that's an assumption we have for black body. And solving this is easy, by the way, right? If you find one of them is black body like this, and if you know the view factors, areas, temperatures, you have two simple equations. With J1, J2, you have to use your calculator like in 1 minute, find the answer.
All of that, and you have 3 minutes per question.
Exactly. Some of the problems like this are time consuming. This is one of the time. And thermodynamics, same thing. If you get a steam cycle, you have to really think it. Now this is what you need to know for any form. Now over here, we're talking about different configuration, and once we know this is easy to understand it. I'm glad we did this. So I guess bottom line is two types of resistances are there. For each surface, you should assign one of those, and this is black body. And for any two surfaces involved, it takes one of those. Question? If there's not, then I'll move on with this and resolve some examples. So if you have a two-surface enclosure, so if you have the net heat transfer due to radiation between two diffuse gray surfaces. This doesn't say enclosure, but I'm pretty sure this is number for enclosures. So if you have a two-surface, net radiation. So let's assume we have something like this, and we have another surface like this. Surface 1, and this is surface 2, right? You can treat it as an enclosure, and here it says it shouldn't be necessarily enclosure, which makes sense as well. It doesn't need to be. Now in this case, if you show those resistance network, take time to do this, but the net rate of heat transfer between surface 1 and 2, or Q dot 1, 2, is equal to sigma T1 to the power of 4 minus T2 to the power of 4. Remember, all those temperatures should be in Kelvin. You can't put C raised to the power of 4. And divided by the resistances in between. I'm going to write it down, but can you tell me how many resistances you think you're going to have between these two? Two surfaces facing each other. Based on the previous example we saw. How many resistances do you think we're going to have if it is 3? So 3 resistances. One of them, so he said you're going to assign a surface resistance to each surface. So 1 minus epsilon 1, A1, and 1 minus epsilon 2, A2. That's for each surface, and then a view factor between two surfaces, which is 1 over A1, F1, 2. And now we solve the previous one. Now we can see that top, the numerator is nothing but the net rate of J1 minus J2, or EB1 minus EB2. And the denominator is the total summation of resistances in between. I mean, it's even easy to remember. I mean, I would remember. I would memorize it. Now, do you want to do one example based on this equation, which I have it here? I mean, once you have it here, it's easy, but it's not a bad idea. So example, 2, maybe that comes on our final, don't tell your friends. 2, next week, 2 plane radiating surfaces separated by a vacuum phase by vacuum, face each other. So that vacuum means that there's no convection in between each other. Each surface has emissivity of 0.02, so they are same. The areas of surfaces are large. So from this large, you should learn something. Are large, there's a hint here, and equal. One surface is at 400, so let's say T1 is 400 Kelvin, and the other surface is at 300. And T2 is at 300 Kelvin, so we know temperature, we know emissivity, we know area to some extent. The view factor, F12 for 400 Kelvin surface, for 400 K surface is 1. By the way, maximum view factor is 1, right? View factor goes from 0 all the way to 1. Most nearly, what is the net heat transfer per unit area from 400 Kelvin surface? Net area from, basically find net heat transfer per unit area from 400 Kelvin surface. So first of all, we know that this is a 2-plane surface, so this will work because this is based on 2 surfaces and separated by vacuum, no convection. We know emissivity, we know everything else.
So we just draw it the same way as that.
Exactly. For this, I'm gonna go ahead and use the same equation, even I don't need to draw the network. For more complex, you have to draw. So exactly, so for here, I would say Q dot between the 2 surfaces are, quickly here, sigma T1 4. And this is exactly this, so I even don't wanna write it down. So this is exactly this. Sigma T1 4 minus T2 4 divided by 3 resistance added together. Now I'm looking for net heat transfer per unit area. So I'm gonna show it with the lowercase q, q dot, which is Q12 divided by area, and area of surface 1 because it's 400 Kelvin, so that we call it surface 1. Which basically here it means that because all the areas are the same, A1 is equal to A2, and they cancel out each other. And since it's based on the area, you can assume area is 1, or simply divide all sides by area, so you get rid of those because it's on denominator of the denominator. So my new equation would be denominator is the same, sigma T14 minus T24, that's the numerator. So on denominator, I have 1 minus epsilon 1 divided by epsilon 1 plus 1 over F1 2 plus 1 minus epsilon 2 divided by epsilon 2. By the way, F12 is, what is F12? It's given 1. The view factor is given 1, so this is just simply 1. So I can simplify this as this. This is equal to, and you should have your calculator ready for those. So sigma is 5.67 times -8. And temperature of 1 is 400 Kelvin, so it's already in Kelvin. For temperature of surface 2 is 300 Kelvin to the power of 4, divided by 1 minus epsilon 1, which is 0.02 divided by 0.02. And by the way, epsilon 1 and epsilon 2 are the same. So I simply multiply by 2, right? Because I have 1 here, 1 here. And then I have the view factor 1, which total is 1. If you do this, your Q12 would be, you have a number? 10.02 watt per meter square. And the multiple choice, I have 4, 6, 8, 10, so I will pick answer D, which is 10, which is close to this. Now, sometimes it's hard to remember this. Of course, in FD you have your PDF file in front of you, but I'm not sure. That's why we need to print them. Did you ask me or somebody else?
I asked you.
Okay. Exactly. I will find it. I was trying to find it, but I was behind today. So it's nice to know if this is inside that solution or not. It's not really, for a 2 surface enclosure, there should be 3 resistances. If you do memorize on top, net rate of power, or just remember this. Let's see.
So if there are 3 surfaces on here,
3 surfaces? This is exactly what we saw for 3 surfaces. This is 3 surfaces, which means 3 nodes. 3 surfaces because I have 1 radius, 1 IR here, 1 absorber. Remaining, I showed you 1. That's what it was of the room. So I have 3 surfaces, and it's more complex as we see.
so it's 6 resistances would be, and then one of them is black bodies. So.
Exactly. So one of them was black body, but you can't simply show it in this nice form. Why? Because some of them are parallel, some of them are series. You have to depend on which one. That's why for that you have to kind of know the basics. Or just, if you kind of review those equations we're talking here, like shortcut equation a few times, especially before the exam, and it's really easy to remember this equation. Now, next one is net radiation heat transfer between two parallel plates. Figure 21.2 with radiation shield. Okay. Now, sometimes to reduce the rate of radiation, they put those shields in between, so it can reflect maximum to the source of heat, so the other side remains cool. Now we're going to kind of talk about that, which is a very typical case for question. First, I write the equation, but I can quickly show you how it's easy to understand this. I mean, I can show the network as well. Now, the next one is if you have the radiation shield between parallel plates. So first, let me show you exactly what I mean. If you have two surfaces parallel to each other, you know how to solve this. This is exactly the previous example, right? There are two surfaces, so we should assign three resistances, one surface resistance to each, and then one view factor in between. But now assume to reduce the rate of heat transfer between the two surfaces, we're gonna put a very thin but highly reflective shield in between. Now it's more than two surfaces. What happened here is that this surface, let's call it surface 1, with the area of A1, temperature of T1, and emissivity of epsilon 1. This surface is area of A2, temperature of T2, emissivity of epsilon 2. And the surface in the middle, we know the area is, we can call it A3, temperature, we can give it one temperature, which is typically unknown, we have to find it. But emissivity of the two sides are typically different, or totally different than epsilon 1 and epsilon 2. So you have to know what is the emissivity of E31 and what's the emissivity of this side, which we call it E32. Now, this almost looks like you have four surfaces. Why? Because I have one surface here, one surface, the left-hand side of this shield, another surface you can assume the right-hand side of this shield because the emissivities can be different, and another last fourth surface is the right-hand side. Now, how many resistances you think will be in this thermal circuit? One, two, three, four, five, six. There you go. Exactly. So first, I'm going to show you the final equation that, based on this kind of quick test book, either you want to remember or there should be on that formula sheet you can find out. So Q dot 1 to 2, or the net rate of exchange between surface 1 and surface 2, when we have a shield in between, right, is equal to net rate of emissivity powers, which is sigma T1 in Kelvin to the power of 4 minus T2 in Kelvin to the power of 4, and divided by the total resistances in between, that is said is equal to 6. One of them is emissivity resistance of surface 1. So 1 minus epsilon 1 divided by epsilon 1 A1. Another one is the view factor resistance between the surface 1 and the left-hand side of the shield. which is 1 over A1 F13. The other is the surface resistance of the left-hand side of the shield. 1 minus epsilon 3, 1 divided by epsilon 3, 1, A3. The other one is the other side of the shield with surface resistance. 1 minus epsilon 3, 2, epsilon 3, 2, A3. A3s are the same, other side. The other one is the view factor between these two, which is 1 over A3, F3, 2, and finally, I have the surface resistance of the surface 2. See, that's really fun. So if I'm going to show it, I have this. This is one resistance because of the surface. This is another resistance because of the surface. This is one resistance because of the surface. This is another resistance because of this surface. And with different color, I'm going to show the mu factor resistance between each two as well. Right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, you should know this equation somehow. Now that we did one first example, you should be able to say, hey, we have two surfaces, so there should be 6 number of resistance in between as what you said really. And numerator is typically this format. The denominator, just adding all of those together, it's kind of easy to remember. So that's what I'm saying.
So like an easy way to remember how many resistances there could be.
Exactly, and the numerator is this is the typical format. So if it's in this format, as long as you can tell what types and how many is, and all you need to know is what is the vicinity of surface 1, 2, 3, U factor, areas, and then just substitute find the net rate from 1 to 2.
I didn't hear. Did you say there's like an easy way to kind of tell how many resistance?
So the easy way is just by knowing. So this just by what we did today. We know that per each surface, we have to assign one surface resistance. So that means 1, 2, 3, 4, all 4 s. And between each two surfaces, there's one mu factor, so total is 6. I mean, based on this. Not too easy, but it's easy. So once you know this is you got it. I mean, solving example on this is exactly the same as before, as long as you have numerical values. You can do this. You have 10 more minutes. Now there's another case, which is the last important case in radiation in this type, is that if you have a re-radiating surface, imagine on those ovens or furnaces, if there's a good portion of heat, they re-radiate another surface with a very shiny coating, so all the heat can come back again to this side. The other side of that shiny surface is insulated, so that's good for re-radiation. What happened if you
statement for that said that there's a radiation field or like there's a reflective surface in between them?
on this one?
Yeah.
There's no, so on this one, that's a good point. Just write some keyword. Figure 21.2, which is this figure, illustrates two parallel plates that are separated by a thin internal shield. So you have to look for the keyword shield for this case. That one is keyword re-radiating. The significance of the shield thickness is that the thin shield has no mass and cannot store any thermal energy. The significance of being a low acidity shield is that the corresponding reflectivity is high, so you can reflect. That's a good way for insulating. If you have an oven and then a room to be air conditioned, so you want to really separate those, make sure you don't add extra heat over there. Most of the energy intercepted by the shield is reflected back to the source. And so this is the shield. Now, in a few minutes, let's talk about last case, which is radiation with reflection. So reflection is a keyword, or also called as re-radiation. You can kind of assume something like this. If you have two surfaces like this, so this is surface 1, A1, T1, emissivity 1, this is A2, T2, emissivity 2, and then the last surface, you want to insulate the outer side of it, insulate it. And the inner side is, we are showing as area of re-radiation, or A sub R, temperature of re-radiation, or TR, and emissivity of that surface. Now, first let me write the final equation, and let's reverse engineer it. So if you're looking for net rate from surface 1 to surface 2, which is this surface to this surface, Q1 to 2, I have on numerator, of course, I have a difference between the net and difference between the emitting powers, which is P1 to the 4 minus T2 to the 4, because I'm showing, I'm going to find out the net rate between surface 1 and 2. And on denominator, I have 1 minus epsilon 1 A1, plus a big resistance, which I'm going to talk right now, and then 1 divided by 1 minus epsilon 2 A2. And that big resistance in between is nothing but 1 over A1 F12 plus, in the bracket, I have 1 over A1 F1R plus 1 over A2 F2R. So this is how it looks like in terms of final form. Now, if you find out how exactly we find this, I can show it. Anyone can guess? So one surface resistance by surface 1, another surface resistance by surface 2. In between, typically we have 1 over A1 F2, but here we have few more terms, which is probably because of this third surface. Now, if I'm going to quickly show this, show the network, and in a few minutes we should be done, is that this is radiosity of surface 1, right? So this is 1 minus epsilon 1 divided by epsilon 1 A1. This is J1. This is radiosity of surface 2. So this is J2. And then there is a surface resistance, go back to EB2, and that's equal to 1 minus epsilon 2 A2. In between these two, different color, I'm going to show another resistance, which is U factor resistance 1 over A1 F12, right? Now what happened for this surface is that same thing, I should assign one radiosity to this. Let's call it radiosity of surface R. And then surface resistance for that. So I have EBR 1 minus epsilon R divided by epsilon R A R. And then I have two view factor resistance because it's facing to two surfaces, surface 1 and surface 2. Makes sense? So quickly on this, 1 over A1 F1R and the other one as well. But the point here is that because we said the back side of it is insulated, no Q can be coming into this, right? That's the definition of insulation. So QR, if this is QR to this EV power, that's 0. Or bottom line is that for this case, because it's re-radiating, we can show that the radiosity of this is equal to EBR, almost like black body assumption. So surface R is presumed to be well insulated and convection effects are assumed to be negligible. Therefore, QR is equal to 0, which means that the net radiation transfer from surface 1 must be equal to the net radiation transfer to surface 2. So because back of it is insulated, whatever heat goes in is coming back. So this is not radiating any power from itself. It's just transferring by reflection. That's why no Q is coming into this. And assume you have a resistance in electrical that you have one voltage on one side of it, the other side is not even part of the voltage difference. So there's no really current going through this. So there's no current going through this. So JR is nothing but EVR, which is almost looks like you see it as a black body. That's another way to put it, right? So you have JR because you know that temperature. And if that's the case, if this is 0, that's why this is basically this, and these two are series but parallel to this. That's why we show it in this form. If you're curious how we found this, because I have these two added together, and I assume if there's no this resistance, I don't want to erase it. If this is plus this is this, and both of them are parallel to this, this is how you would show it. Now again, even this is easy to remember as long as we know the logic. Does this make sense? Of course, we can solve an example on this, or we can talk more about this. But if there's a question, I can answer. I know you guys are sleepy. Otherwise, I'm sleepy too. No, I'm not sleepy. Otherwise, we can start up here, which is all this works is covering. So, which is really all we have here as well. And we should be able to solve any net radiation problems with this. Yeah, absolutely. Especially knowing that the one basic one we did for, if you have 5 surface enclosure, it doesn't matter, it's the same thing. Of course, they limit what they want from you because you can't really solve it in 2 hours. But you know exactly how it works. On this, we can talk more or do more examples. But bottom line is that we radiating, the backside is insulated, no heat is added. So really no heat is going through this. So you can ignore this, which is almost looks like black button. That's it. Question for me, let me know. Otherwise, I'm gonna stop recording this.